It's funny. Usually when you think about feeding yourself or maybe feeding a pet, you naturally think about whole foods.
Right, yeah.
You think about a rich, complex diet full of different ingredients.
Yeah.
But then the moment you step outside and decide to feed the plants in your garden, it's like, well, it's like you suddenly act like an astronaut or something.
Oh, totally.
You just hand your tomatoes these sterile, isolated, neon-colored powders or, liquids from a plastic jug.
Yeah.
It's like you expect an entire vibrant ecosystem to thrive on the equivalent of a chemical protein shake.
Yeah, it really boils plant health down to this highly engineered artificial formula. I mean, industrial agriculture basically strips away all the biological complexity that took billions of years to evolve.
Exactly.
And it just says, here is your synthetic fuel, now force yourself to grow.
Right. Which brings us to today's topic. Welcome to another deep dive. Today, our mission is to explore a project that completely flips this whole chemical approach on its head.
It really does.
We are looking at this ingenious project by two students from a Nature and Innovation class, Kesser and Steen. So, they are currently building a tiny forest for you, something about the size of a large kitchen garden, and they're using the famous Miyawaki method.
But with a really rebellious twist.
Yes, a huge twist. They are completely redefining what fertilizer actually means, and they are doing it entirely with natural stuff, basically just scavenged from around their neighborhood.
Yeah, the contrast is what makes their approach so fascinating to me. Because, well, before they can even think about planting trees, they have to feed the soil, right?
Right.
And conventional farming approaches this by obsessing over three little letters, N, P, and K, nitrogen, phosphorus, and potassium.
The holy trinity of industrial fertilizer.
Exactly. I mean, a conventional farmer takes a soil sample, looks at those three isolated metrics, and then just dumps synthetic fossil fuel-derived versions of them right onto the dirt.
But wait, why those three specifically? Like, I see NPK on the bags at the hardware store all the time, but what do those elements actually do for a plant?
Well, they're basically the foundational building blocks for different biological functions. So nitrogen, the N, is crucial for building the chlorophyll molecule.
Okay, so making things green.
Right. It's literally what makes a leaf green and allows it to capture sunlight. If a plant lacks nitrogen, it just turns yellow and stops photosynthesizing entirely.
Oh, wow. Okay, and the P, phosphorus?
Phosphorus is all about energy transfer and root development. It helps form ATP, which is basically the cellular battery of the plant.
Got it.
And then potassium, the K, acts kind of like the plant's immune system and fluid regulator. It actually controls the opening and closing of these tiny pores on the leaves called stomata.
Which stops it from drying out, right?
Exactly. It literally prevents the plant from wilting during a drought.
Okay, so plants undeniably need those three things. That makes sense. But, I mean, a wild forest obviously doesn't have a chemical factory pumping out synthetic blue crystals. So how does nature actually source its NPK?
Well, the sheer scale of nature's supply chain is just mind-blowing. Let's look at nitrogen first. We burn incredible amounts of fossil fuels to manufacture synthetic nitrogen.
Right.
But the atmosphere that you are breathing right this second is actually 78% nitrogen gas.
Wait, really?
Yeah.
78%?
Yeah.
Yeah.
And in a natural system, specific soil microbes and fungi literally just pull that nitrogen straight out of the air. They break the chemical bonds and feed it directly to the roots of plants.
That is wild. They just pull it out of thin air.
Literally.
Okay, what about phosphorus then? Because that's a heavy mineral, right? It can't just float in the air.
Right. So in the industrial world, we mine phosphorus out of rocks using heavy machinery. But in a natural ancient forest, it arrives through these massive global cycles.
Like what?
Well, phosphorus gets swept up in windblown sand from deserts, and it actually travels across entire oceans while you sleep, eventually settling onto distant forests.
You're kidding.
Nope. And it also moves through animals. Like, imagine a bear catches a wild salmon that has spent years in the ocean, right? That salmon has been accumulating phosphorus from microscopic sea life. The bear eats the salmon in the woods, and then its droppings deposit that heavy mineral right onto the forest floor.
Oh, wow. So it's this massive interconnected web of life moving nutrients around the globe.
Exactly. Which actually brings up a huge logistical problem for Kesser and Steen.
Right, because they want a thriving forest, which means they desperately need potassium, that fluid-regulating K element.
Yes, and potassium salts are highly soluble. They wash away really easily in the rain. So if these two students absolutely refuse to buy synthetic fertilizer from a store,
Which they do.
right, and they're working on a $0 student budget, How on earth do they source potassium?
Well, they look at their local geography, right?
Exactly. They realize the nearby beach is basically a giant repository of soluble minerals that have washed into the sea.
I love this part.
So they literally just walk down to the shore and scavenge washed up seaweed and eelgrass that's just lying right there on the sand.
It's so smart.
Yeah, because seaweed acts as a biological sponge in the ocean, pulling in massive amounts of potassium and trace minerals.
Who, let me make sure I have this right. Instead of buying expensive chemical supplements from a garden center, they're basically foraging a free beach smoothie multivitamin for their dirt.
A beach smoothie. Yeah, that is a great way to visualize it. It's dense, it's local, and it costs them absolutely nothing but the calories it takes to carry it back from the beach.
I just love the hustle. But applying this beach smoothie brings up a huge operational question. Because usually when city planners or developers try to build a new urban green space, the very first sound you hear is the backup beep of massive diesel dump trucks.
Oh, absolutely.
They bring in heavy excavators, they truck in tons of commercially packaged compost and straw.
And the carbon footprint of that standard approach is just staggering. I mean, Kesser and Steen look at all the diesel being burned just to prep a site, and they realize it completely defeats the whole purpose of planting a forest to capture carbon.
Right, it's totally counterproductive.
So they rely on what the sources call the lasagne-metode, combined with a practice known as chop and drop.
The lasagna-metode. Okay, so they are layering.
Exactly. Instead of tearing up the earth with plows, which, by the way, destroys the existing soil structure, they just layer gathered organic material directly on top of the lawn they want to replace.
So they wander their neighborhood gathering, what, autumn leaves, grass clippings?
Yeah, weeds they've pulled up, hedge trimmings. They basically mix all of that scavenged neighborhood quote-unquote waste together with their seaweed.
Okay, I have to stop you there because if my neighbor started piling up dead weeds, grass clippings, and slimy seaweed on his front lawn, I definitely wouldn't call it a forest in progress. I'd call it a garbage dump.
Right. It sounds a bit messy.
How is this pile of yard waste supposed to turn into a pristine forest floor?
Well, you have to fundamentally reevaluate the definition of trash. In a forest, a fallen leaf is not garbage. It is literally the architectural foundation of the next generation of life.
Okay, fair point.
And to trigger that transformation, Kesser and Steen cap their messy layer of yard waste with a very specific type of wood chip. They actively seek out ramial chipped wood from local arborists.
Ramial wood. How's that different from just, running a dead tree trunk through a wood chipper?
Oh, it is biologically night and day. Ramial wood comes from the young, green branches and twigs of a tree, usually anything under about 3 inches in diameter.
Right.
A thick, heavy tree trunk is mostly heartwood, which is essentially just dead, crystallized carbon used for structural support. But young twigs contain the cambium layer.
Living part.
Exactly. That is the living, breathing, active part of the tree. It is packed with proteins, enzymes, nitrogen, and minerals. And arborists are usually thrilled to dump these fresh twig chips for free just to save themselves a trip to the municipal recycling center.
Oh, that's brilliant. Free delivery.
Right. So the boys take these rich green chips and layer them thick right over the lasagna pile.
And that heavy layer of wood chips immediately blocks out the sun, which means the old lawn grass underneath is going to start dying.
Yes.
So what is actually happening down in the dark under those wood chips to turn that garbage into soil?
Well, we are basically looking at a microscopic battleground between the greens and the browns.
Sounds like a sports game.
Kind of. The dying grass and the seaweed, that is your green material. It is packed with very simple, easy-to-access sugars, nitrogen, and proteins.
Okay.
The heavy layer of ramial wood chips on top is your brown material, which contains incredibly complex carbon structures. The moment that grass is starved of sunlight and begins to die, the first responders of the biological world show up.
Bacteria.
Bacteria.
Because bacteria love easy sugar.
They absolutely gorge themselves on the simple sugars leaking out of the dying grass. This rapid, frenzied consumption creates a massive amount of metabolic heat.
Oh, like a compost pile.
Exactly. If you stick your hand into a fresh pile of decomposing grass, it is physically hot to the touch. The bacteria rapidly break down the green material, releasing a flush of nutrients.
Yeah.
But very quickly, the bacteria hit an impenetrable wall.
What stops them?
The wood chips. Specifically, a complex organic polymer inside the wood called lignin.
Lignin.
Yeah, lignin is the biological armor that makes wood stiff and rigid enough to grow hundreds of feet into the air. Everyday soil bacteria simply do not possess the biological tools to break those rigid lignin molecules apart. To them, a wood chip is basically like a piece of concrete.
Wow. So if the bacteria tap out, the whole decomposition engine just stalls. Who steps into the ring to break down the wood?
The true heavyweights of the forest floor, fungi.
Mushrooms.
Well, specifically specialized white and brown rot fungi. These organisms secrete incredibly powerful, targeted enzymes that act like microscopic chemical scissors,
Snipping the concrete.
snipping the complex lignin polymers into smaller, digestible carbon fragments. And as the fungi eat the wood, they grow into this massive, intricate underground network of thread-like structures known as mycelium.
So this mycelium is basically a subterranean highway system being built in real time.
It is a living internet for the soil. The mycelial network physically connects different areas of the forest, transporting water, sharing nutrients, and even sending chemical warning signals if a plant is being attacked by pests.
That's incredible.
It is. But building this vast highway requires energy. And here is where Kesser and Steen's biological hack really reveals its genius. Fungi need nitrogen to power the enzymes that break down the carbon in wood.
Okay.
Because the wood chips themselves don't have quite enough nitrogen to fuel this massive expansion, the fungi actively scavenge available nitrogen from the surrounding topsoil, temporarily locking it up inside their own fungal bodies.
Okay, wait. Locking up nitrogen sounds like a massive problem. If I'm trying to grow something, I need that nitrogen in the soil, not locked inside a fungus.
You'd think so, but
Hold on. Kesser and Steen don't have trees planted yet. They are just trying to kill the old lawn and prep the site. Are they actively trying to rob the soil of nitrogen?
think about what happens to the seeds of all those aggressive weeds buried in the lawn when the nitrogen suddenly disappears.
Oh my gosh. Without nitrogen, the weed seeds have no fuel to sprout. They're basically starving out the competition.
It is supreme natural weed control. Opportunistic weeds require a huge rush of free nitrogen to explode into growth. Because the fungi are hoarding it all to digest the wood chips, the weed seeds are basically trapped in a temporary nitrogen desert.
That is so smart.
And by the time the boys are actually ready to plant their trees, the fungi have finished breaking down the wood. The fungal network dies back, releasing all that stored nitrogen back into the dirt.
Like a slow-release fertilizer.
Exactly. But now it isn't a volatile chemical that can wash away in the rain. It has been transformed into a stable, spongy, carbon-rich matrix called humus.
Humus. Wait, like the dip you eat with pita chips?
No, spelled with one M, Humus.
Ah, gotcha.
It is basically the holy grail of soil science. It is organic matter that has been broken down to its most stable microscopic form. It acts like a powerful sponge, holding onto water and nutrients so they are available exactly when the tree roots need them.
Okay, so the biological engine is humming, the weeds are starved out, the soil is turning into this rich humus. Now they are finally ready to plant their tiny forest. And you mentioned earlier they're using the Miyawaki method, which has a very specific style of planting, right?
Yeah, Akira Miyawaki was a Japanese botanist who observed that natural forests surrounding ancient shrines grew in a very distinct way. The Miyawaki method replicates this by planting native tree species incredibly densely, sometimes 3 or 4 saplings per square meter.
That is dense.
Yeah, and this intense crowding forces the young trees into a race for sunlight. They shoot upward rapidly, creating a thick, closed green canopy in just a fraction of the time a normal plantation would take.
It sounds incredibly efficient. But as Kesser and Steen look at standard Miyawaki forests, they apparently spot a massive ecological flaw.
They realize that while a traditional Miyawaki forest gets you a green canopy very quickly, it completely lacks structural maturity.
What do you mean by that?
Well, if you walk into a truly ancient, natural woodland, it isn't just a clean grid of upright, healthy young trees. A real forest is chaotic. It is littered with decades, even centuries, of accumulated dead wood.
Like fallen logs and stuff?
Exactly. Massive fallen trunks, shattered branches, ancient rotting stumps. That decaying wood is a vital, functioning organ of the ecosystem. But traditional urban forestry usually skips this entirely. They just plant saplings on a flat, cleanly prepped bed of dirt.
So how do 2 students hack the timeline to give a brand new patch of dirt the maturity of an ancient woodland?
They actively introduce deadwood on day 1. As they plant their young, densely packed saplings, they strategically wedge thick, heavy branches and old rotting logs right into the soil between the trees. They refer to these logs as biological anchors.
Biological anchors. It's almost like it's like building a brand new house, but deliberately furnishing it with 50-year-old antiques.
Oh.
They're literally dropping an ancient architecture for the ecosystem.
That is a brilliant analogy. And these antique furnishings serve incredibly specific biological functions. First, a rotting log is a giant, slow-release water sponge. But more importantly, it provides instant habitat for the heavy lifters of the decomposition world. The sources specifically highlight insects like the stag beetle.
Oh, stag beetles. They look like little armored tanks with massive antlers. How do they help a forest grow?
So the adult stag beetle is impressive, but the real work is done by the larvae. A stag beetle larva will spend 3 to 7 years living entirely underground, completely blind, just chewing its way through dead wood.
Wow, just chewing for years.
Yeah, they act as biological plows. As they chew, they grind the tough wood fibers down, and the bacteria in their gut ferments it. They essentially turn solid logs into nutrient-rich sawdust, inoculating the soil with beneficial microbes as they move. You simply cannot have a robust population of these vital decomposers if your forest is nothing but clean soil and tiny saplings.
So by dropping in those biological anchors, they are sending out an immediate eviction notice to the lawn insects and like a VIP invitation to the heavy wood decaying crew.
Exactly.
But you mentioned those logs acting like sponges, which brings us to the most terrifying threat for any young urban forest.
Yeah.
You can plant all the dense saplings you want, but if a summer drought hits, those shallow little roots are going to bake and the trees will die.
Oh, absolutely. Watering a forest is a massive challenge. The industrial solution is to trench the site, lay down miles of ugly plastic irrigation pipes, hook it up to the city's treated water supply, and run it on a computerized timer.
Very expensive.
Very. And Kesser and Steen just reject all of that. Instead, they look at the natural elevation and the contour lines of their terrain, and they employ 2 ancient earthwork techniques: swales and hugelkultur.
Swales. Let's look at the physics of how that actually works.
All right, imagine a gentle slope. When a heavy rainstorm hits, the water rushes downhill instantly. It erodes the topsoil, strips away the nutrients, and disappears into the nearest concrete storm drain before it can soak into the earth.
Right.
A swale is designed to intercept that rushing water. It is a broad, shallow trench, dug perfectly level, running horizontally across the slope. It strictly follows the natural contour lines of the hill.
So because the bottom of the trench is perfectly flat, gravity can't pull the water sideways anymore. It basically acts like a giant speed bump.
Exactly. When the sudden downpour rushes down the hill, it hits the swale and just stops. The water pools in this long, flat basin. Because it can't flow left or right, it has absolutely nowhere to go but straight down.
Oh, I see.
It is forced to sink slowly and deeply into the subsoil.
Okay, so the swale forces the water underground.
Yeah.
Where does the hugelkultur come in?
So, hugelkultur is a German term that translates roughly to mound culture. Just downhill from the swale, the boys dig a wide pit. They fill that pit with massive amounts of bulky, organic earth logs, heavy branches, the roughest wood chips they can find.
More dead wood.
More dead wood. Then they pile the excavated soil back on top, creating a raised berm or mound over the buried wood. Finally, they plant their Miyawaki saplings directly onto and around this mound.
Wow, I'm trying to visualize the physics here. The heavy rain hits the slope. It gets trapped in the level swale trench. It sinks deep underground, and then it immediately flows downhill into the buried logs of the hugelkultur mound.
Yes.
It's like they're engineering an enormous subterranean sponge. Like an underground wooden camel's hump storing water for the trees.
A giant wooden camel's hump is the perfect way to describe the synergy. That buried wood soaks up hundreds of gallons of trapped rainwater and holds it tight. Months later, during the scorching dry weeks of late summer when the surface soil is completely baked and cracked, the young trees are perfectly fine.
Because their roots are deep.
Exactly. Their roots have grown down into the mound and they just drink steadily from that buried, waterlogged wood sponge.
But the wood isn't just holding water, right? Because it's buried in damp soil, it has to be rotting.
Oh, it is actively composting. And the sheer mass of that buried wood composting generates a gentle, continuous ambient heat deep in the soil.
Oh, a built-in heater.
Yeah, this subtle underground radiator actually extends the growing season for the trees into the autumn. And simultaneously, as the fungi and stag beetle larvae break down those buried logs, they release a steady, slow drip stream of essential nutrients directly into the root zone of the young canopy.
It honestly leaves you a little speechless when you step back and look at the whole system. Compare this to, a landscaper on a gas-powered riding mower dumping synthetic blue crystals onto a perfectly flat, sterile lawn. Kesser and Steen have proven that fertilizer is not just a commercial product you buy in a plastic jug. It is a dynamic, interconnected biological engine.
They really stepped completely outside the mindset of trying to forcefully control nature. I mean, they scavenge a free beach smoothie of seaweed for potassium. They use the nitrogen-stealing power of fungi to starve out competing weed seeds. They hack the structural timeline of the forest by dropping in ancient logs as biological anchors.
Right.
And they engineer these brilliant, drought-proof camel humps to capture every drop of rain. They simply observe the incredibly sophisticated mechanisms that nature has perfected over billions of years, and they arrange the pieces so those biological processes can thrive.
It's so impressive. And it leaves you with this really lingering, provocative thought. If two students on a $0 budget can engineer a drought-proof, self-fertilizing, incredibly complex ecosystem just by observing how nature works and rearranging the neighborhood's natural trash,
Yeah.
what other waste in your modern everyday life is actually the exact fuel you need to build something resilient? Maybe it is time you stop looking for sterile, perfectly packaged solutions in plastic jugs and start looking a little closer at the messy, brilliant, untapped potential sitting right under your feet. You know, it's funny. Usually when you think about feeding yourself or maybe feeding a pet, you naturally think about whole foods.
Right, yeah.
You think about a rich, complex diet full of different ingredients.
Yeah.
But then the moment you step outside and decide to feed the plants in your garden, it's like, well, it's like you suddenly act like an astronaut or something.
Oh, totally.